Hello everyone. It's 7:31 in the morning. You wake up and before you even leave your bed, you reach for your phone. Nothing unusual. It looks like just another ordinary morning. But before the next few minutes are over, something extraordinary is going to happen again and again and again. Your phone looks at your face and it unlocks. You open maps and within second you can find the routes. You can rotate your photograph, you can even zoom in and out. You open your Netflix or any streaming app, and somehow it seems to know what you might enjoy today. All of these feels completely normal, right? And perhaps that is the strange part. We have become so used to these things that we rarely ask how they are actually possible. Now imagine something changes. Your phone can no longer recognize your face. Mass map receives information but cannot make sense of where you are. Recommendation become almost random. Google search engines they struggle to decide what result deserve to appear first. The internet is still there, the software is still there, the machine are still there, but something underneath them is missing. What? Look at these problems carefully. Moving an image, finding a location, predicting what someone might like, or deciding which information is important. They appear to belong to a completely different worlds. Photography, navigation, entertainment, the internet. So here is our first mystery. Are these really different problems? Or are we looking at different version of the same idea? Start with something ridiculously simple. Suppose I give you one point and ask you to move it. Easy, right? I tell you where it is, I tell you where it should go. Done. There is almost nothing interesting here. But now, what if I stop giving you one point? What if I give you 10 point, 100,000, 100,000 points? Eventually, those points could become the pixels of an image. And a modern image may contain millions of them. We all know that pixels are the building blocks of image. Now I ask, rotate all of them, or stretch all of them, or reflect all of them. Move everything correctly at the same time. Would you really want to tell every single point where to go? Of course not, right? That would be a madness. So perhaps we are asking the wrong question. Instead of asking where should each individual point move, we should ask is there one rule that the entire collection can obey? One rule like millions of points, and suddenly a problem that looked impossible large becomes structured. And that idea is going to appear again and again today. Whenever complexity becomes overwhelming, look for the rule underneath it. Let's understand with example. Consider a photograph. To us, it is a mountain, a person, a memory. But digitally, it is an enormous collection of tiny pieces of information. And yet your phone can rotate it, stretch it, you can reflect, you can tilt it almost instantly, right? It does not need to invent a separate instruction for each of the pixels of that image. Instead, what we do, we describe a transformation, and that transformation rule the entire image obeys. So, our first challenge is how can one rule move an entire world of points? Remember that question. Now, leave images completely. Imagine you are standing somewhere in a city. A satellite sends information. Does that single piece of information tells us exactly where you are? Usually not. It gives us a clue. Another satellite gives another clue. Another gives another. Separately, each clue may be incomplete, but together something remarkable happens. The possibilities they begin to collapse until eventually one location survives. So the second challenge is very different. How can several incomplete pieces of information by each satellite can be combined so that they all agree to a common location? Let's move to the third problem. Now forget the location. Suppose I show you two people. One loves Interstellar, Arrival and Inception, and another loves Interstellar, The Martian, and The Gravity. You might immediately say that their taste is similar. Fine. But what exactly does similar mean? And what does when there are not three movies but thousands of movies? And not two people but millions of people? A machine somehow has to turn something as vague as taste into something that can be compared. That gives us our third mystery. Can similarity itself be measured? Now, what matters the most? Let's consider one more scenario. Now, imagine the web, billions of pages, billions upon billions of connections between the pages. You search for something. How should that Google search engine or any search engine decide what deserves to appear near the top? Suppose one web page is mentioned by 100 unknown websites, another is mentioned by only 3 websites. But those are extremely trusted and influential websites. So, should 100 beat 3? Probably not. And now we encounter a strange circular problem. A page may be important because important pages points to it. But how do we know which pages are important in the first place? How do we find what matters inside a gigantic network of web pages? This is the fourth scenario. And let me present you one last scenario, which is my favorite one. Imagine a robotic arm is holding a glass, and the glass must remain perfectly still. But suddenly, there is an obstacle near the elbow of the robot, and the robot needs to move around it. The hand cannot move because that glass must remain at the same place. So the hand cannot move, the glass cannot move. But the rest of the robot must. At first, that sounds contradictory, right? How can something move without moving what matters? Like without moving the actual hand, how we can move some parts of it only? And yet, robots can exploit exactly this kind of hidden freedom. So, our fifth problem becomes what can change while the final result stays exactly the same? Now look again, a photograph, GPS, recommendations, search engines, robotics. These are 5 different technologies, 5 different stories. But underneath them, something is beginning to repeat. We keep asking questions about many quantities at once, rules that act on entire collections, combining information, comparing objects, finding important structure, and discovering what can change without affecting what matters. So perhaps these problems are not strangers after all. Perhaps they share a hidden language. And this is where the real difficulty begins. Human beings have always worked with numbers. One quantity is easy, 10 is still manageable, 100 is still possible, but modern problems are different. Thousands of measurements, millions of pixels, millions of users, billions of connections among the web pages, and often these quantities they are not independent. They influence one another. The challenge is no longer simply what is this number, it becomes how do enormous collections of quantities they behave together. That is fundamentally different kind of problem. And there is another difficulty. We look at a face and see a person. We hear music and feel the melody. We look at a map and see a place. We watch a film and experience a story. Machines do not begin with these meanings. They begin with numerical representations, pixel measurements, signals, ratings, coordinates. So, if a machine is going to reason about the world first has to become something numerical. Then only it can understand our world. There is an old philosophical idea about people seeing shadows and mistaking those shadows for reality. Computer sleeps in a strangely similar situation. The photograph is not the person, the waveform is not the music, the coordinates are not the city, the numbers are not your taste in movies. They are just representations, numerical shadows of something richer. And this creates a beautiful question. How much can we understand about the real world by learning how to work with its numerical shadow? And now the pattern becomes clearer. Again and again, modern problem asks us to do four things: represent something complicated in a useful form, transform that representation, compare it with others, and simplify enormous amounts of information without throwing away what matters. Represent, transform, compare, simplify. Different applications, right? But the same recurring actions. This is the engine that has been hiding behind everything we have seen. So now we can begin asking the questions that will drive our course. Suppose one object has several measurements. It can have height, weight, speed, temperature, brightness, maybe 100 more measurement it can have. Do we really want to treat every measurement as an isolated number, or can we package many quantities together and begin thinking about them as one mathematical object? That simple questions opens an entirely new way of describing information. Next question. Suppose something changes. It rotates, stretch, moves, changes its description. Does everything about it change? Not necessarily. If something changes, does everything about that particular thing change? Not necessarily. Something sometimes the most interesting part of a transformation is discovering what survives it. What can move, what can change, and what remains fixed. This idea appears everywhere: geometry, physics, data, computation, robotics. Sometimes understanding a system means finding what changes. Sometimes it means finding what refuses to change. Now we are finally ready to give this language a name. The language that let us describe many quantities together, transform entire collection systematically. It can combine constraints to give a final answer. It can measure similarity. It can discover hidden structure and understand what can change while something else remains fixed. That language is linear algebra. It's not about simply matrices or simple calculation. It is not about just rows and columns on a page. These are the pieces of the notation. The deeper subject is about the structure, transformation, information, and relationships. And that is how I want us to begin this course. Not by memorizing a definition, not by collecting formulas before we know why they exist. First, we'll understand the problem, we'll build the intuition, we'll see what the mathematics is trying to solve, and only then we will learn the language. But mathematics becomes much easier to remember when you first understand why somebody needed to invent it. So, from here onward, whenever you see a vector, a matrix, a space, a transformation, a basis, or eigenvector, these are the terminologies that we study in linear algebra. Whenever you heard these terminologies, don't begin by asking what formula should I use. Ask something more important. What problem is this idea trying to solve? Feel the need first, learn the language next. Welcome to linear algebra.